We all know AI can do some incredible things, right? It can generate unbelievable art, write code, basically act like a genius assistant. But it has a pretty big secret. Underneath all that brilliance, these AI models are absolute memory hogs, and that's creating a massive traffic jam for the future of AI. Today, we're diving into a huge breakthrough that just might clear the road.
So here's our game plan. First, we're going to really unpack this big memory problem AI is having. Then, we'll take a look at the old way of trying to fix it and why it didn't quite work. After that, we'll meet our hero, TurboQuant. We'll peek under the hood to see its secret sauce, look at its real-world report card, and finally, connect the dots on why this could honestly change everything.
All right, so let's get right to the heart of it. AI's amazing intelligence comes at a price, and that price is paid in memory. And this isn't just some abstract problem for computer scientists. It's the reason your favorite AI tool might feel sluggish, or why you can't run the most powerful models on your own devices.
To get its head around, well, anything, an AI uses something called high-dimensional vectors. You can just think of these as the language of AI. It's how a model captures all the nuance and complexity in an idea, whether it's the meaning of a sentence or every little detail in a photograph.
Here's the catch, though. These vectors are massive. They take up a ton of memory, and that's creating a huge bottleneck. It's like a rush hour traffic jam inside the AI's digital cheat sheet, what's known as the key value cache. And when that gets all clogged up, everything just grinds to a halt.
Now, this isn't a new problem. People have been trying to fix this for a while. So let's look at one of the first big attempts, which, had a pretty major flaw.
The main idea was something called vector quantization. It's a classic compression trick. The logic is simple. If the data is too big, just shrink it, right? Save space, speed things up. It totally makes sense on the surface.
But here's where it went wrong. This old method actually created its own memory problem, an overhead. Think of it like a processing tax that ate up a chunk of the very memory savings you were trying to get. It was like trying to save money, but your bank charges you a huge fee to hold it. Kind of defeats the whole purpose.
And this is where our hero, TurboQuant, enters the scene. This is the breakthrough that figures out how to get all the amazing benefits of compression, but with, you guessed it, none of the drawbacks.
The goal here was really the holy grail. Could we get massive data compression, making everything way, way smaller, but without losing even a tiny bit of the AI's accuracy? It's the absolute best of both worlds.
So how on earth does it actually pull this off? Well, it's not magic, it's just really, really clever math. Let's get into the two-step takedown that makes TurboQuant work.
It all comes down to a brilliant 1-2 punch. First, it uses a super high-quality compression method called PolarQuant. And then for the knockout, it uses another technique called QJL to clean up any tiny lingering errors.
Okay, this first step, PolarQuant, is all about looking at the data from a new perspective. Instead of saying go 3 blocks east and 4 blocks north, it says go 5 blocks total at a 37-degree angle. It's a much more direct, more efficient way to describe the exact same point.
And this little trick is the key. By thinking in terms of angles and distance, the model gets to completely skip a really expensive and time-consuming step. And poof, that memory tax we talked about, it's completely gone.
So that's step 1. Now for step 2, the cleanup crew, QJL. This part is just ruthless efficiency. After that first big compression, QJL comes in and reduces every single number down to its most basic form. Is it positive or negative? A +1 or a -1? That's it. This makes the data incredibly light.
So QJL is basically a super fast spell checker for math. It zips through and corrects any tiny little errors left over from step 1, making sure the final result is dead-on accurate. And the best part? It does all of this with absolutely zero memory overhead. It's a cleanup step that costs nothing.
Okay, that all sounds incredible on paper, but the proof is in the pudding. So how does TurboQuant actually perform when you put it up against the competition in real-world tests? Let's take a look.
Take a look at this. This chart shows performance on what's called the long bench, a tough test that pushes AI on all kinds of tasks. And I mean, the results speak for themselves. In question answering, summarizing, coding, that TurboQuant bar is just towering over the others.
And it gets even crazier. They ran these needle-in-a-haystack tests. This is where you ask the AI to find one tiny, specific fact buried in a mountain of text. TurboQuant found it every single time. Perfect accuracy, while making the data at least 6 times smaller. That's just wild.
And what about speed? This one number pretty much says it all.
On some of the most powerful computer chips out there, TurboQuant made a core AI calculation up to 8 times faster. Not 10% faster, 800% faster. That's a massive leap.
This incredible efficiency also shines in vector search, which is the technology that powers the most advanced search engines. And what do we see? Same story. TurboQuant is just better at finding the most relevant results, leaving the other methods in the dust.
Okay, so let's pull back from all the charts and numbers for a second and talk about the big picture. Why is this more than just a cool technical achievement? Why does this really change the game for the future of AI?
So what's the bottom line here? It means search gets way faster and smarter. It means we finally unclog that huge bottleneck at the heart of large language models. It means the cost of running powerful AI goes way, way down. And it does all of this while delivering top-of-the-line accuracy at a level of efficiency that was practically unheard of.
And look, this is the really crucial part. This isn't just a clever hack that might break tomorrow. As the researchers themselves point out, the math behind this is rock solid. These methods are provably efficient, which means they're built on a foundation you can trust for the biggest, most important systems in the world.
And that brings us to the final thought. What we're really seeing here is the removal of a fundamental roadblock, memory and cost, that was holding AI back. So it really makes you wonder, if AI can now be smaller, faster, and smarter all at the same time, what's the next impossible problem it's going to solve?